half of that thing
Oh,
over
you're
1
good.
and minus 2x.
I'll just leave a little blank right here for everyone. Right now, you know, that's the tough part, isn't it?
Yeah.
We're gonna go off to the side. Make sure we nail this n prime. We're saying n is a 4r squared minus x squared to the 1/2 per r, right?
Mm-hmm.
And don't think you gotta differentiate that r, just think of some constant. We're just trying to find what's the derivative of n with respect to x. So in fact, maybe I should write it like that. I know I always just write n prime, but that's what I'm saying. I don't want you to think you gotta differentiate with respect to r. We're gonna write this answer in terms of r. As the radius of any circle, right? So, 1/2 in front.
Mm-hmm.
Decrease all this by 1. Chain rule. The derivative of this would be 0.
0
We're thinking of that just some constant radius.
minus 2x.
Minus 2x. Now, is anything sweetened up there?
You can cancel out the 2.
Right there? What's going to happen is we're only differentiating. Great question. That's going to be confusing about this problem in relation to the others. Because we're writing this in terms of some radius r, right? When they started out, this problem, they didn't say a circle with radius 10 or anything, did they? So what we're going to do is we're going to write this final answer in terms of the radius. That's what we'll do. So this r is just going to be, part of the answer. So because we're only differentiating with respect to what letter? X. Now if this said dndr, you're right. You were right if it said dndr. We're just differentiating with respect to x. So we're like, oh, you're not x. So the derivative of u will be just what? 0. Now, what can I do with that 2 and that 2?
You can
Cancel.
cancel.
Again, it looks like x over square root 4r squared minus x squared. All right, let me put it in.
Oh, that should be negative x, Professor.
Yes,
Oh, thanks. And this up here one. Thanks, Art. He's saying, don't forget, there's a little, see it? Don't forget that little negative. So that's not x minus x, that's x times a negative x. Let me put it a little higher, make sure it's x times negative x. So let me write this again. We've got a prime equal to negative x squared over square root of 4r squared minus x squared plus this. Now how do I get this as one solo fraction? I need common what?
Denominator.
I need common denominators, right? Don't I? I'm going to set this equal to 0, but I want to get one solo fraction out of this. Can I erase that?
Mm-hmm.
Are you sure? Amber, can I erase that? That was the work to get that derivative, that hard derivative. Yeah?
Yeah, you agree.
Alright, I'm going to get common denominators, and I think you all can see it. To add these together, I just have to multiply what over here?
That.
Another one of these, right? So when I do that, you got this a prime equal to negative x squared over the square root of 4r squared minus x squared. And then you go plus square root 4r squared minus x squared, and you're saying, hey, just multiply a square root of 4r squared minus x squared over a square root of 4r squared minus x squared. Let me make sure that's a minus. Alright. Looking good. So now, a prime just equals this. And we now have just a 4r squared minus x squared solo in the denominator. What is this times this?
Same, 4 plus 4r square minus x square.
Oh, you need the parentheses. Like terms? Equal to?
0.
Now we're going to solve for x. In terms of r. that numerator. Alright, negative 2x squared equals negative 4r squared. Divide the what?
2,
Negative 4 divided negative 2 is?
2. So x equals to root 2.
Plus or minus? Let me know if you think this could be negative.
No, it cannot be because has to be distance.
X has to be distance. Look at our image, gentlemen. Right, we got geometry over here. X has to be the distance inside. Take off the minus. And if you want, what's the square root of an r squared? Square root of 2, I gotta leave square root of 2, but what's the square root of r squared?
R.
So I can write this as square root 2 with an r outside only. We'll get this problem wrapped up because you are square root 2r. This will give us the most maximum area. Now, how do we get y? Alright, and when you're going to plug it in right there, okay? We'll get it. We need that y. Let's see. Well, I think it's easier to plug in what? How about we substitute x squared? Right? We're going to leave the answer in terms of r, Amber. But, don't you agree if I'm trying to substitute this in here to get the y, I could just substitute that x squared right there. What's x squared equal to? 2r squared?
Sure, yeah.
I'll put that right there. Y equals the square root of 4r squared minus
2r squared.
2r squared.
So y
Alright.
equals 0.
4r squared minus 2r squared is?
2r squared, sorry.
And you're like, optimization, you get a lot of symmetry. You get a lot of symmetry. What does this simplify to be? And you're like, oh my gosh, are you kidding me? Right? That rectangle is really a what? Square. And that's what she's saying. She's like, in optimization, even though it could have been a what? This rectangle, you go, that was what? That was my intuition. You know, her intuition was, this is Kelly, it should be a square. Right? This side equals that side. And you're getting a square. This rectangle they mentioned at the beginning, they didn't use the word square, but it's going to be a what? It's a square. You get a lot of symmetry in these answers when you try to optimize something. Like that, make it a cube. In this case, it becomes a square. What's the dimensions of the square? Square root of 2r by a what?
Square root of
Square root of 2r. So I didn't draw it to scale. I did that on purpose just to think, hey, all we got is a rectangle, because that's what they said at the beginning. And let me go back to the question, make sure we answer this. Find the dimensions of the rectangle of largest area that can be inscribed in a circle of radius r. Well, the dimensions are square root of 2r by square root of 2r.
2r squared.
Right? Right? And those are the dimensions. It's a square. It's a square with the side length of what? Square root of 2 times radius. Isn't that cool? So now I want to apply this. You're designing something, and when your radius is 10, you got to get the square inscribed in there with maximum area. Guess what you do? Square root of 2 times what? 10. By square root of 2 times 10. Does that make sense? Just to see an sometimes you want to see an example. All right, here it is. Right? And when there's your circle, this is 10. All right, what would be the dimensions of that rectangle that gets the most area inside of here? What would it be? This dimension would be
square root of
square root of 2 times a what?
r.
Yeah? What would this dimension be?
Same.
Or Amber, what if this radius was 20? This side would be what?
Square
20
root of
squared root of 2. This would be what?
20 square
20
root.
squared. You see, we go on and on and on. We wrote our answer in terms of radius now because it could be any size circle. Isn't that cool? No matter what, that's how you make it. You get the most area out of that square. Cool stuff, though. But did you notice there's always symmetry? Oh, it's a square. Keeps going. That box, remember the box? It was 20 by 20 by 10. And if you put a top, you put a lid on a thing, you get a cube, you know? It's either 20 by 20 by 20, or 10 by 10 by 10, or 30 by 30 by 30. Cool. Good deal. Hey, you ready for Newton's method?
Mm-hmm.
All right, this section rocks. What have you been doing the whole time, Josephine, with that calculator? It's so cool, it just solves what? Equations? You're gonna find out why. You're gonna know, you'll know exactly what kind of program is this thing running through? How is this thing solving equations for me? You know, outside the typical quadratic formula and stuff, right? So, I made a worksheet, just so we can write, so it's fun to work through. We're gonna solve this equation, I'll put it on the board and I'll pass this out. Oh, this is so cool. Just the idea behind this. Brilliant. Brilliant idea. Hey, everyone, throw that question at your friends who are engineers and all that stuff. Just say that to them. Go, hey, listen, I got a problem for you. Go what? I got a math problem for you. Find the dimensions of a rectangle, all right, of largest area inscribed in a radius. I mean, not inscribed in a radius, inscribed in a circle. And see if they can come up with it. You remember the answer. What was the answer? The dimensions are what?
Square root of 2.
Square root of 2r by a square root of 2r, it's a square. Let's see if they can come up with it. They'll start out probably thinking, oh, I can do this, but see if they can come out and get the answer. You know, they might use geometry or something like that, but calculus always works. Here's the equation we're going to try to solve. And when we're done, we'll be accurate to many decimal places. Now, I have to point out the answer is irrational. You know, that's not quadratic form, that's x cubed. Sometimes there's more than one answer. So, how do you solve something like this? We're going to solve this by Newton's method. All right. And after we work this worksheet, we definitely will just make up another equation, and we'll solve it. We'll do something similar. The first thing is we want to look at this graph. That's what Newton does. Newton's method is like, I want to think of how this graph is. I want to see where this thing, y equal to x cubed plus x minus 1. All right? So, you could sketch it. You could sketch the graph. Anybody want to graph it right now with your graphing calculators? You got it? Where is it crossing around the x-axis? Just give me ballpark.
Like 1.
She goes close to 1. It's crossing the x-axis. So feel free to graph that thing. Y equal to. Now she knows how, and a lot of you in this class know how to use a calculator to solve this using that tool. But what you're going to understand is a process it's going through. It's going through like an algorithm, like Newton's method. I can't guarantee it's Newton's method because I don't work for TI. Maybe they use another approximation technique. You know, maybe there's another technique out there that's a little more elegant for this problem. Am, did you graph it? Good. So now I get to pass these out. I made the graph myself, but I enlarged it. I wanted to focus in so you and I can draw lines and stuff. So I really kind of enlarged the image. Huge. I used Maple software to make this graph. I'm like, here's the curve. I stretched it out with decimal points and stuff. There you go. You're welcome. We'll write on this. You can write all over this. Anybody wants an extra copy, let me know. To know Newton's method, we gotta draw like segments and tangent lines and things of that sort. So that'd be easier this way. Give your Jeff. You bet, man. You're welcome. You're welcome, Dale. Well, I like when you said it was close to 1. There you go. Because that's going to be our first guess. We always start with a guess. I don't know if you've noticed, every time you run through the calculator to solve something, you've hit like a left bound or a lower bound. Have you noticed that? Right? Yeah, it does this guess thing. That guess thing is like this. You have to tell the calculator, like at least make a guess to get the thing started. We're going to do the same thing, Ellen. A good guess here, Josephine came up with it. It was like, this thing was close to around x equal to 1. All right, well, let's try 1. Maybe x equal 1 works, okay? So I'm going to guess x equals 1. That's my guess, right? X equal to 1. What I want, is it the answer, is 1 cubed plus 1 minus 1 equal to 0?
No.
No. Sorry, didn't work. That's okay, but we're gonna start with that. So let me get this graph here myself. And I see it's cutting around, I don't know, like 0.6, 0.7 over here, right? All right. But if we guess x equals 1, and when you and I think of this curve, y equals x cubed plus x minus 1. If we guess x equal to 1, that's right here. Now when an x equal to 1, what's the y value? 1, does everyone agree? You plug 1 in here, you get 1. But we're going to start with that with our guess. So, I would like you to start filling out this little table here. So when our first guess is going to be the 1, I put the 1 there, does everyone see that? Well, what's the y associated with that going to be?
1.
So we got this little table going, we're like, all right, x, 1. Y is 1. Our goal in this algorithm, this process, is to turn that y value into 0. Do you agree? We're going to run some iterations. But our goal is to eventually get this to be a what? 0. If that's 0 and we have a number here, that's our answer, right? Because y would be 0. Does that make sense? All right, we do that. Now, this is brilliant. I love this idea. Newton decided, hey, to come up with this answer, you make a guess. Okay, it's not perfect, right? Then you draw a tangent line. From that point where you made your guess, then you draw a tangent line. Okay, so let's just do your best job of making like a tangent line right here. What would it look like? I don't know, it'd do something like this, wouldn't it? Something like that? Go ahead and do it. I like drawing that curve. Doesn't have to be perfect, but just draw like a tangent line. Just make sure it hits the x-axis. That's what's important to me. Draw a tangent line, but make sure it hits the x-axis.
But here's the